Okay, let's talk about ionic bonding and ionic compounds. Ready? So what happens to valence electrons in an ionic bond? Well, the valence electrons are transferred. So you can see in this GIF, sodium Na gives an electron, loses an electron. Chlorine gains an electron. So the electron is actually transferred. It leaves sodium and goes to chlorine, and then they end up with charges, and then there's an attraction. So the transferred electrons give each ion a stable octet, 8 valence electrons. Remember the exception, it's 8 valence electrons or 2 total electrons like helium. So by giving up an electron, sodium ends up with 8 valence electrons. By gaining an electron, chlorine ends up with 8 valence electrons. So cations are positive. That means the atom loses electrons, like sodium did in our example. Those elements that lose electrons are metals. So if you look at the oxidation states on the periodic table, you can see these end up with positive charges, indicating they're losing electrons. Here's a hint. Cations are positive. There we go. So cations are positive. So cations are positive. So cations are smaller than the parent atom, which if you think about it makes sense because they're losing an electron. If you lose an electron, your size is going to get smaller. So you can see that visual right here. Here's also what I want you to see, that as an atom, sodium has 11 protons and 11 electrons. So its overall charge is 0. When sodium loses an electron, notice its size got smaller, but also you notice that the number of protons did not change. It still has 11 protons, but now it does not have 11 electrons, it has 10. So when we add these two numbers, remember protons are positive and electrons are negative, we have a positive 1 overall charge. Okay. Now, the electron configuration, because now sodium has 8 valence electrons, it's stable and it matches that of a particular noble gas. Which noble gas would it be? Well, it would be the one that has the same number of electrons, right? Because the number of protons defines the element. So 11 protons is always sodium, but 10 electrons. What does that configuration look like? Well, it looks like not helium, but neon. So sodium's electron configuration when sodium becomes an ion looks like neon. So when lithium becomes a lithium ion, so here's lithium, its electron configuration matches what noble gas? Well, lithium loses 1 electron. So instead of having 3, it has 2. So lithium would match helium's electron configuration. When potassium becomes a potassium ion, its electron configuration matches what noble gas? Well, here's potassium right here. Its oxidation state says +1, so that means it loses 1 electron. So instead of having 19, it has 18. So potassium would match argon. All right, now what about anions? Anions are negative. These are atoms that gain electrons, and they tend to be nonmetals. So a lot of nonmetals have a lot of oxidation states. You can see, especially look at nitrogen, the giant list of charges. But for our purposes for this unit, all you're going to do is look at the very first oxidation state. Later in the year, we're going to get to what the rest of these are. But for now, we're just looking at the first oxidation state. And you can see that that is negative for all of these nonmetals. Here's our hint. Remember, cations were positive. Well, an ion is a negative ion. An ion, a negative ion. So remember, we start with an atom, and if we lose electrons, we form a cation with a positive charge. And if we gain electrons, we form an anion with a negative charge. So anions, because they gain electrons, end up larger than their parent atom. So here we have chlorine. See how it has 7 valence electrons. This is a chlorine atom. It has 17 protons and 17 electrons. That's why it has a balanced 0 overall charge. When it becomes a chloride ion and gains an electron, now it has 8 valence electrons, but the number of protons and the number of electrons is not the same anymore. So it has 17 protons, or 17 positives, and 18 electrons, or 18 negatives. So we end up with a -1 overall charge for the ion. So when nitrogen becomes a nitride ion, its electron configuration matches what noble gas? Well, here's nitrogen. Its oxidation state is -3. That means it gains 3 electrons. So it started with 7, it gains 3, it ends up with 10. So its electron configuration for the ion matches neon. What about when chlorine becomes a chloride ion? What does its electron configuration will match what noble gas? Well, here's chlorine. It has 17 electrons as an atom. Its oxidation state is -1. That means it's going to gain 1 electron. So its electron configuration when it becomes an ion will match argon. Ionic bonds then form because of the strong attraction between positive and negative charges. So one atom lost an electron, became positive. One atom gained an electron, became negative. And now positive and negative attract each other. And that bond is so strong, okay? So something else to just to have tuck this away in your head to remember. Monatomic, remember, means one atom. Polyatomic, poly means many. So we can have ions that are made from one single atom. So a chloride ion, for example. But it can also happen sodium, calcium, aluminum, chlorine, oxygen, nitrogen, elements on the periodic table. So one single atom loses an electron, or one single atom gains an electron, or more than one electron. Okay. Polyatomic ions, those are 2 or more atoms that are bonded together, and they are bonded together with covalent bonds, but then they end up with a charge, okay? So these are sort of unique. When you see a polyatomic ion in a compound, well, you know it had an ion, so it has ionic bonds. Those are super strong, but the polyatomic ion itself is bonded with covalent bonds. So it's going to end up with both types of bonds, ionic and covalent, in the same thing. Here are some examples. You do not have to remember them. Luckily, you have table E on your reference table to show you all the polyatomic ions you need to know. And here they are. So here are the polyatomic ions on table E. You can see that some of them are positive, most of them are negative, okay? Remember, the atoms in a polyatomic ion are covalently bonded to each other, but because they have a charge, they are then ionically bonded to something else. So let's look at some properties of ionic compounds. Ionic compounds are also called salts. So ionic bonds, remember, form between an anion, which is negative, and a cation, which is positive. Stuck together, strong bond. The anion is usually a nonmetal. The cation is usually a metal. But remember, it can involve polyatomic ions. States of matter. Well, ionic compounds or salts are solids. They have a regular crystal lattice structure. So all of the ions are bonded to each other. So we have a positive sodium and a negative chlorine bonded to each other, but then there's all kinds of sodiums around all kinds of chlorine, so they are kind of connecting to each other. Conductivity. Well, ionic compounds are weird. Okay, so as solid. So if I shook some salt just on the table, had a pile of salt. Conductivity is low. It's not going to conduct heat or electricity. But if I could melt it, or if I took it and dissolved it in water, it does conduct electricity. And here's why. So as a solid, those bonds between those sodium ions and those chloride ions is so strong. So there's no movement allowed to conduct the electricity. But when I melt it or dissolve it in water, those ions kind of can move a little bit, okay? So when it's melted, the ions can move. If it's dissolved, the ions can move. So it's going to conduct electricity, conduct heat as well. Is it malleable? Is it ductile if it's an ionic compound? Nope, not at all. Remember, malleable, hammered into thin sheets, ductile, stretched into wires. Now, their melting points and boiling points are high. And when we do intermolecular forces, we'll talk about this again, but because they have strong intermolecular forces, so their melting and boiling points are high, so it takes a little bit more to get them to break. And that's it. There's ionic bonding and ionic compounds, and I hope that you learned something new today.